Okay, so I'm creating this video because I want you to have this in your Google Classroom because this is a resource that you can use if you don't understand the topic. The other day I was explaining how to calculate the ideal and the actual mechanical advantage of an axle and wheel, which is an example of a simple machine. As usual, half of the class wasn't paying attention. And then when you had to solve the problem, you don't know what to do. And I had to repeat all the information. And I have to write the questions in the chats of the live session. Today I'm not doing that because I'm creating this video so you don't understand the topic. What are you going to do? You're going to refer to this video. Yeah, I'm going to start with a review of what you were learning last class. We were talking about wheel and axle. And you know that in a wheel and axle, this shaft over here that you have there, that's the axle. And this over here, yeah, that's a wheel. Okay? Remember that we're learning about, I have said this like 1,000 times. And you're learning about simple machine because in engineering we use simple machine just to do more work with less energy. Remember, the title of this unit 1, is energy and power. If you're using less energy, that means that you need less power. Okay? One of the job of the engineers is to do more with less. Just keep that in mind. Okay, now in this presentation, okay, the one that was creating this presentation was using a triangle for the fulcrum. Okay? And they are comparing the wheel and the axle with a lever. You know that you have the fulcrum over here, and then you have a distance there in which the resistance and the effort force are gonna be applied. Okay, which one, Ms. Ramos, is the resistance and the distance? We don't know. That's one of the things that you have to take into consideration when you're solving a wheel and axle problem. Now, what is the difference between a lever and a wheel and axle? That in the lever they're talking about linear distance, and wheel and axle they're talking about circular motion. Okay, if the shaft is moving, you know it's gonna be following a circular pathway. Ramo, what are you explaining that one more time? Because in order to write the ideal mechanical advantage equation, they were using the circumference equation. Okay, remember the circumference is giving you the linear distance of a circle, and the equation for the circumference is 2 pi r. This 2r, okay, twice the radius is the diameter. So if you have the diameter, circumference is pi multiplied by the diameter. Okay? Questions about that? No, but you have the diameter of the axle, and then you have the diameter of the wheel. And they are doing, this, or they are writing this ratio. The ideal mechanical advantage is the effort diameter over the resistance diameter. By applying the circumference equation, see, diameter of the effort, diameter of the resistance, they were substituting there the formula for the circumference, and they were simplifying until diameter of the effort, they got that equation. And you have that 2 examples over here. 2 examples over here. Let's say that the diameter of the axle is 6 inches and the diameter of the wheel is 20 inches. Your first step is to identify who is doing the effort. doing the effort, as you can see over here, less than 1, because the one doing the effort is the one with less diameter, meaning that the axle was the one doing the effort. In that case, you have a third class level, and the ideal mechanical advantage is always less than 1. In the opposite case, in which okay, the effort force is caused by the wheel, always that distance, see, from the center rotational or the fulcrum all the way through, the distance effort always is gonna be bigger than the diameter of the axle, and you're gonna have always an ideal mechanical advantage bigger than 1, because you have a lever type 2. And let me summarize this one more time. When the effort is caused by the axle, you have a lever second class, and the ideal mechanical advantage is always smaller than 1. When the effort is caused by the wheel, then you have a lever. No, you have a lever. Okay, let me say this again. When the effort is caused by the axle, okay, you have then a lever third class, in which the distance resistance is always bigger than the distance force. Okay, so you're gonna have always an ideal mechanical advantage smaller than 1. When the force effort is caused by the wheel, you have a level second class, when the effort distance is always bigger than the resistance distance, so the ideal mechanical advantage is always is gonna be bigger than 1, which is more efficient. Okay. Another example here, but in this case they are introducing efficiency. How you're gonna calculate efficiency is the actual mechanical advantage over the ideal mechanical advantage. What happened with the ideal mechanical advantage? This is the one that you're gonna use to design, okay, the ideal situation. Actual, remember, this is the one that is relating the distance, okay, and diameters in the case of the wheel and axle. This one is the ratio of the forces. The one that is called actual because it's when you have a resistance force in there, then you're gonna be able to see what is the effort force that you need to move that resistance force. It's the one that you get in real life. Ramos, are we gonna be able to use some real life example to see if the simple machine that we have is efficient? Yes. We are gonna create, simple machine. You're gonna be able to add some load in there. You know that the load is the force. Okay, now what are we going to be using? We're going to be using change like quarters and pennies. You know the quarters, they weigh more than pennies. If you put 4 quarters in one, let's say in one side of your lever, and then you have 3 pennies, the 3 pennies, they are able to move the 4 quarter, you know that your system is efficient, okay? Because with less force, you were able to do more work, okay? And you have an example over here. Now in this example, as you can see over here, okay, the actual, okay, mechanical advantage because they were giving you the forces. But remember, in real life, you don't know the actual until you design your machine, you put your resistance force, and then you measure what is the effort force that you need to move that load, okay? That's a pretty good efficiency, okay, because it's close to 100. Questions about that? No? And as you can see over here, since the ideal mechanical advantage is bigger than 1, is because the effort force was, okay, applied by the wheel. when the F4 force, remember, is applied by the wheel, you have a level second class, and always the ideal or the actual mechanical advantage is going to be bigger than 1, because the F4 force is bigger than the resistance force. And on the slides that we were discussing before, we was just reviewing. That was the class that I was teaching the other day, but I decided just to include that in this video because you were not paying attention. Another example of a simple machine. You have a pulley. What is a pulley? Oh my goodness, Rama, we're gonna continue talking about lever. Yes. See, it's a wheel with a groove in its rim that is used to change the direction and magnitude of forces exerted by a rope or a cable. And you have an example here in this screen that you have there. Okay, so how we're gonna calculate the ideal mechanical advantage of a pulley, how we're gonna calculate the actual mechanical advantage of a pulley. That's what we're learning today. Okay, but before we start learning about ideal mechanical advantage and actual mechanical advantage for pulleys, we have two types of pulleys. We have a fixed one, and then we have a movable one. If you look at this over here, see, fix over here, it doesn't move. This one is between the two cables, moving in there. Okay, and as you can see that we're using the triangle as the fulcrum. Look over here. Okay, this is a lever first class. Okay, and the distance from here to here and here to here the same. Okay, so how you gonna be able to put this resistance force up? By applying the same force. So you're gonna balance with the same amount. The only thing that you're doing is changing the direction of the force. The direction of the forces is the only thing that you're doing there. And then you have the movable one, which is first class over there. See, look at the fulcrum is there. Okay, but this is my low over here, so this is my resistance distance, and this is my resistance effort, because the effort is caused in the opposite direction. That's the second class lever. Always is gonna have an ideal mechanical advantage bigger than 1. It's a forces direction stay constant. Okay, questions about that? No? Okay. Uy, mi Ramos, what is this? Pulleys in combination. So you have a combination of pulleys in there in order just to move a heavy objects. Okay, now a pulley like this, a pulley with that combination, is also called a block and tackle. Why a block and tackle? Because if you follow, I'm gonna use it. If you follow the rope, see, the same rope was used to go through all the pulleys. If that is the case, okay, how you're gonna find the ideal mechanical advantage? Number of strands opposing the force of the load. Okay, so this one is going down, all the other ones they are pushing up. So you're gonna count them 1, 2, 3, 4. That's your mechanical advantage. When do we use pulley in combination, Ms. Ramos? When we want more efficiency. Okay, when we want more efficiency, when we want to use less effort force to put this up. I'm going to introduce, no, I'm not going to introduce a new equation. Okay, by the way, it's not a new equation. You already know this equation because you were working with that equation during all the classes. Actual mechanical advantage, and you know that the actual mechanical advantage is the resistance force over the effort force. Okay? Now, if I want to find the force that I need to move that bicycle, I can use that equation. Why? Because I'm going to assume that the ideal mechanical advantage is equal to the actual mechanical advantage, which is not what is happening in real life, but I'm going to assume that I have 100% efficiency here. So the ideal mechanical advantage is 4, because remember that you were counting the strands that were opposite to that. So I know that my resistance force is 600 pounds. Now I want to find the effort force that I need to put that on that end to move the bicycle. If you isolate the x over here, so you have divided by 4. Okay, by the way, it's gonna be smaller than 600. And that's the purpose of using simple machine. Just to have, just to do more with less. Since over here you need 150 pounds to move this, you will be using less power and less energy when you are using that pulley to move that bicycle. And that's the whole point behind this. Okay, ideal mechanical advantage, you use that, the relationship between the distance, just to design. If you assume that you're gonna have 100% of efficiency, then you can design the effort force that you're gonna need, and then you have to test that in real life. Okay. And madam, what is this? Okay. Now, do we use simple machine in real life? No. We use a combination. Why a combination? Because when we use a combination, we have more efficiency. And then you have a combination over there of if you are assuming that over here he is attached to the level there, you have a fixed, because he's not moving, you have a fixed pulley, and then you have a lever here with, over here you have the resistance force. Okay, see over here, the effort force is going to be applied by the system of pulley that you have over there. Miramos, let's say that we have a system like that. How we're going to calculate the ideal or the actual mechanical advantage of the system, I'm going to teach you how to do that. But this is just an example of how you can combine machines just to use less energy and consequently less power. Is this one. So here you have a pulley and here you have a lever. If you want to calculate that mechanical advantage, you're going to multiply the mechanical advantage of the lever times the mechanical advantage of the pulley. And that's going to be the mechanical advantage of your system as a compound machine. Okay? This is another type of pulley. See, this is not the tackle, the block and tackle that we were using. Why not? Because see, this is the same like a strand, but this second strand is separated from the blue one, and the third one is separated from the other two. See, when you have that combination, how you're gonna find the ideal mechanical advantage? Are you gonna count the strands that you have opposite to the resistance force? The answer is no. You're gonna use the formula. See, you're gonna separate them by system, and then you're gonna count the strands that are opposite to the resistance force. You have 2 on the first, 2 on the second, 2 on the third, and you multiply all of them. So the mechanical advantage is gonna be 8. Okay? Questions about that? No? And Ms. Ramos, with that information, can we calculate what is the... look at the picture, because this picture is interesting. When you analyze the picture, they are putting C. Over here, seeing the mechanical advantages too, you're going to be able to lift 80 pounds with 40. But when you go to the second pulley, you're gonna be able to lift this with 20. Okay, but when you go to the third, the force that you're gonna be using here as the result of the system, 10 pounds. So 8 times smaller. Okay, actually that's the one that is gonna be using the energy. Okay, these pounds, they're gonna be the resistance that you're gonna have on the strand, but this one is the load that you have to use over here. Let's say that you want to put a motor over here. If that motor is giving you 15 pounds, it is more than enough just to put this up. Okay, that's the thing that you have to take into consideration when you're designing a compound machine with 2, 3, or more combination of simple machine. It's just to do more work with less energy. Compound machine. Now, misconception that you make when you are working with pulleys. Okay, the angles, it doesn't matter. It doesn't matter if you have the strand at an angle. That's a humongous misconception. In this class, we're gonna assume that the strands, they are parallel. Okay, so when you look at that, the angle between the two strands is equal to 0 degrees. When you have this situation, you have to apply trigonometry. Do I want to teach you how to work with Sokoto, like with identities? No, trigonometrical identities. No, I don't want to teach you how to do that. If you don't like it, because you're very bad at math, and I don't want just to complicate your life. So we are not touching this. See, examples. Now, in the future, you're going to be designing compound machines. So if you are planning to put a pulley into your compound machine, you have to make sure that the strands, they are parallel. So you can calculate the actual mechanical advantage and the ideal mechanical advantage. Otherwise, you're not going to be able to do that. Or when you do that, applying the formulas that you have learned, you're not going to have a reliable result. Okay? Another misconception that you have. Okay, so when you have a block and tackle, you're gonna count all the strands that are pulling up. Look at the sample that you have there. See, even though you don't have a block and tackle, okay, you have to look at the direction of the effort force. See. You have to analyze. I'm gonna count all the strands that are in there. It doesn't matter if they're going up. No. So you have to identify where the resistance force is, and then you're gonna count the strands that are opposite to that resistance force. That's another misconception that you have most of the time when you're calculating ideal mechanical advantage for pulleys. So always remember that in the wheel and axle, we have to find if the effort force was applied in the axle or in the wheel. Okay, over here for the pulleys, you have to know where the resistance force is. See, any strand that is opposite to that, okay, then you're gonna count them to find the ideal mechanical advantage. This is the last thing that. Oh, Ms. Ramos, now you're introducing efficiency. Yes, I'm doing that. Okay, and this is super important. No, but we are assuming that they are 100% efficient when we are designing. Once that we build our design, we test. Remember, we're gonna be following the design process, and when we test, we are gonna be able to see what are the we know the resistance force. We are gonna be able to calculate the effort force or to measure the effort force. We want that information. We are gonna have the actual mechanical advantage, and we're gonna be able then to calculate the real efficiency of the compound machine. If the efficiency of the compound machine is too low, then you have to redesign your machine one more time. Okay, but you have the equation here, and the equation is the ratio between the actual yes, because the actual always is going to be smaller than the ideal mechanical advantage. Remember this, you measure that. Once that you build your structure, this is the one that you're going to use to design your structure. Okay, Miramos, what are you introducing efficiency? Because after this class, you're gonna be designing a compound machine, and I want a specific efficiency for that machine, and you have to work with those equations. To the picture, you're gonna talk about. Okay, this equation is not new for you because it's in general. Okay, so the actual mechanical advantage is gonna be equal to, let me see, the force, a ver, Miramos, we haven't seen that before. The one that we have seen is this one. Yes. What is the force in? The force that you have to input into the system to move the other one, which is the F of force. What is the force out? This is the load that you're moving because it's causing your resistance there in your system. So you are familiar with this formula. In is the F of 4 because it's the force that you have to input into the system in order to move that force that you have in there, to move that force out. In order to move that force out, input into the system to move this out. Okay, if you want to remember that, but it doesn't matter. It doesn't matter. So it doesn't matter the terminology that you use, as long as it makes sense and is consistent. Okay, the resistance is the force out, the effort is the force in. Okay, now Miramos, why do we have to know that? You forget about the gear ratios because we're going to learn about that later. What do we need to know? How to calculate the mechanical advantage of a compound machine? Because remember, I told you that you are going to be building a compound machine, and I'm going to give you some constraint for that construction. And one of the constraints that we're going to use is the efficiency of the compound machine, and you will have to use all of that. Okay, so I'm been talking to about many things. You're not going to remember anything by the end of the class, but you have the video now just for you to use as a reference. Okay, axle. Let me use another color. All right, this is the wheel. This is my axle. Okay, if we're talking about circular motion, have you heard that? One rotation per second. What does that mean? That this wheel, see, was rotating or was covering, okay, 360 degrees, the entire circumference in 1 second. Okay, what does that mean? That wheel was covering the entire circumference. What is the linear distance? 2 pi r or pi d, which is the diameter of the wheel, in a second. That's why that was rotational velocity is all about. The same happens for the axle, but it depends on the dimension of the axle and the wheel. Okay, so when you're talking about rotations per second or revolutions, they're not talking about Cuban revolution. No, we don't want any communism here. Okay, revolution, they're talking about the linear distance or the angle that is covered, okay, per time, okay, at that given time interval. Okay, so if let's say that the wheel is moving only 90 degrees per second, only, one half of the circumference was covered. So if I want to find the linear distance, I will multiply the pi multiplied with the diameter of the wheel, and then I will divide that by 4, because that was only the linear distance that was covered in that given time. Questions? No? Okay. So now you're ready to work in your class code.